Hi everyone, my name is Maggie, and I'll be your host for today's webinar on SOTA. Today's webinar will be delivered by Ted Driver. Ted joined AGI 15 years ago and develops AGI's analytical services and writes analysis algorithms for SDK components. He also develops tools for space object and missile threat analysis.
Thanks, Maggie. So as Maggie said, my name is Ted Driver. I've been at AGI for quite a while now, and as I was putting these slides together, I just started to think about the fact that this year is the 50th anniversary of Apollo 11 landing on the moon. And it really got me to thinking about the fact that we really have kind of conquered space now. It's easy to get to space and use it for business. Satellite costs are way down. Launch costs are also down. We're down to less than $10,000 per pound to get to orbit. The number of satellite launches are also growing. So in 2017, there were 90 launch attempts. As I was gathering stats for 2018, I found out that it increased to 114, and also found out that China has now surpassed the US in the number of launches. And so we've conquered space, and that means that everybody is conquering space. So because we've conquered it, space is relatively safe. Once your mission is in orbit, it's pretty safe up there. We, over the last 60 years of being a spacefaring people, have figured out that there are dangers up there, and we figured out what those technical challenges are and how to fix those. We've radiation hardened our parts. We've figured out how to get power and store power on satellites, and how to dissipate heat once it builds up in the satellite. Our satellites are lasting longer. Some of the GPS satellites that I know about are at least double their design life. Some are longer. And then the higher your orbits are, your satellites are going to be up there for many, many years. So space really is safe. That is until recently. So space has been safe, but as it becomes more accessible, new threats have emerged. And unfortunately, your spacecraft really now is at risk from other space objects. So space is kind of like the old port town where you knew everybody in town and you knew what they were up to. But as that town grew into a city, you don't really know everybody in that city anymore and what they're doing. So there's people in space now, similarly, that we don't really know quite what they're up to. There could be threats up there that might be affecting our missions, and it'd be nice to know what those are. Even if you have been paying attention, you might have noticed that some of those are getting close to you in orbit. This issue has been acknowledged. The recent push, for example, to create a space force emphasizes the need for threat assessment in space. General Hyten, the commander of STRATCOM, has stated that speed is required to stay ahead of this multi-domain threat. This really is going to allow us to protect our defensive opportunities for response. And so being fast at understanding these threats is really a need. So how can you know what an adversary is up to? Let's look at some of these threats. The threat is real. You may have heard of the term for the satellite Luch Olymp that is up in GEO right now. Typically, when you're in GEO, you stay in your slot. In fact, by definition, that's what the GEO belt is for. You go up there so that your satellite isn't going to move with respect to the Earth. So if you see satellites in GEO that are moving, why are they moving? What's going on? What's their purpose? Recently, Russia, last June, launched a satellite that we call the Russian nesting doll satellites. Once the satellite was on orbit, it opened a port and a smaller satellite was ejected. And then that smaller satellite opened a port and a third satellite was ejected from that. So there's this Russian stacking doll mechanism going on for satellites from that launch. CNN has covered the issue if you want to look that up. There's the Chinese SJ-17 launch that happened. It's another GeoSat, a technology demonstration satellite. They have moved close to and performed proximity operations on different satellites 2 or 3 different times now. And so we're not really sure what's going on with that satellite either. So looking at these threats, if we want to assess what they are, it really requires sifting through millions of possible trajectories to find those that might be the most imminent threat to satellites we may care about. So what's our need here? We need to assess threats to objects in space from other space objects. And for our purposes here, threats arise from space objects that do the following. They need a small delta V to reach another space object, or they can reach that other space object quickly. So if either of those constraints is met, we should consider that a threat, a possible threat to us. A solution to this need would be that we have to assess all possible threat paths, finding the most likely. We want to know what those threat paths are. We also want to look at the objects in all orbit regimes. If you're in LEO and think maybe that you're safe from an intercept from a GEO, do you know if you are? Could something happen to your space asset in LEO from a GEO satellite? We want to know that. We want to look at multiple threat actors against multiple space objects. You may have one satellite that you're interested in and possibly one threat that you're curious about. But what happens when you have many satellites you're interested in and there might be multiple threats? You want to be able to assess those situations as well. And then you want to be able to provide a risk-based valuation for each pair of the space objects you've analyzed. This is really important when you start looking at just tons and tons of data that comes out of the calculations. You want to be able to know quickly which satellite pairs are the ones that most at risk and which ones you should pay attention to. Finally, you want to be able to express your results in plots and orbit displays and reports so that you can take that data and analyze it for your operations and prepare for a defense if you need to do that. So really the challenge in this need is that there are hundreds of millions of calculations that are required, and they must be done quickly in order to preserve your defensive operational timelines. That's a big challenge. So what I want to do is I want to share a couple of screenshots of the Space Object Threat Assessment tool that we've developed here. This first screenshot, I'm going to go over and show you the main panel of the SOTA tool. Notice on the top, there's an Analysis tab and a Results tab. We're on the Analysis tab now. There's a time and duration box in the top left where you set your analysis time, the start time, and then how long you want your analysis to run. So you may only be interested in the next 4.5 hours, for example. That's the duration there. There's a threat details box at the bottom where you set your engagement type. I'm going to show you some of this in the demo as well, but right now it's set at intercept. You can also set this to a proximity to assess if this threat was going to come up and start performing proximity operations against your satellite. What sort of delta V's would it need to be able to do that? So you can set the engagement type to proximity to find that out. And then there's two boxes on the bottom. One says chase vehicles, one says target vehicles. So in the chase vehicles, you can click the blue add vehicles button and add satellites. And for our picture here, we've got one in there. That is represented by the green orbit and the globe above. I'm sorry, the red orbit and the globe above. That's the chase vehicle. The target vehicle is represented by the green orbit there. And so this is a one-on-one analysis. So if we were to run this in the tool, we would go to the results page, and then there's a couple of different tabs here. Vanguard, which I'll talk about in a minute. Then there's a chase/target, which gives you different plots that shows you information about this particular encounter. And then the orbit tab, which shows you the visualization. And I've stopped it at the time where the chase is just about to intercept the target vehicle. There's a row at the bottom that shows information about this particular intercept. So the delta V to intercept in meters per second was about 257 meters per second here. There's a delta V to prox. Notice that, I'm going to go back one slide here. Notice that this is a pretty complex LEO case. The chase vehicle is in a certain orbit, but that orbit is definitely different than the target vehicle. It's out of plane. It's something you may not expect a threat to come from because you might be assuming that you have to do a plane match in order to be a threat to the target. That's not necessarily true, as you can see here on the results page. With a delta V of only 257 meters per second or so, that chase vehicle can intercept that target vehicle. And as you can see here, no plane change was involved with that. And so we also give you the time at intercept at the bottom of the row here as well. So that's the results tab for the one-on-one. And I did talk before about the fact that you need to analyze millions of different orbits and do millions of calculations to find out which orbits are the ones that are going to result in the minimum delta V required that your chase vehicle might be using to intercept you. So let's talk about those orbits for a second. In this picture here, the Earth is in the middle, and this just shows a representation of the different types of orbits we're taking into account when we're looking at ways the chase vehicle can intercept your target. So there are direct ways. You go from start to finish in a direct manner without going around the Earth. So there's no revolutions around the Earth. Or you can go around the Earth maybe once or twice or many times before you intercept the target. Each one of those requires a different delta V, and we look at many different types of orbits like this to understand which one has the minimum for the case you've outlined in the tool. So just to give you a visualization of what this looks like, I'm going to start a video playing here. This is a video of all possible orbits for a single pair, colored by relative time of flight. And so in this particular example, we have a satellite, the chase satellite in low Earth orbit, and the target satellite in GEO. Each of the dots you see coming off represent one of those orbits that we're testing for its minima capability. The colors of the different dots coming off are relative time of flight values for that particular time of departure. So when that maneuver happens, the colored dots are representing the time of flight for that particular maneuver. And so you can see that all these dots represent maneuvers from the chase vehicle as they're traveling to the target vehicle at GEO. And they all do intersect that target vehicle. All right, so now let's look at some results. What I'm showing you now are the exported results from the SOTA tool. I'm going to show you a demo of SOTA as well. I'll show you how to export the results, and you can share these with anybody, so they don't necessarily have to have the SOTA tool to understand what you're seeing. But what we're looking at here, these two graphs, the one on the left is a heat map, the one on the right is a surface plot. They're both the same data. Let's talk about the heat map on the left. Each one of the pixels in this graph was one of those dots on the video we just saw previously. And each one of those is an orbit that we tested. If there's no dot there, it means that no orbit is possible there. But a few things stand out in this plot, and that's the blue areas, and that's where the delta V, which is represented by this color band here, is minimum. So we have a delta V, this is in kilometers per second. So a color of blue is about 1 kilometer a second. And so these particular times are interesting times because they tell us when a minimum amount of delta V is required to intercept my vehicle. So I've got, from a million different calculations or so, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different times when a minimum amount of delta V is required to intercept me. And that's actionable information right there. Just to make sure everybody understands this plot, let's talk about the axes here. On the bottom is departure delay in seconds, and this is the time that the maneuver starts from your analysis start time that you set in the tool. So if your analysis start time started at midnight and your delay was 2,000 seconds, that's when the maneuver happens, 2,000 seconds after your analysis start time. The time of flight is the y-axis, and that's how long it takes for the chase vehicle after its maneuver to intercept your target vehicle. And so you can see with those different combinations, we calculate the delta V for those. We get that information out that's very helpful. And the surface plot is a nice way to visualize those low delta V wells as well. So it's another nice option to have. So that is that complex LEO to LEO case that I talked about. Let's look at a new case, the Hyo to Geo example. So here, we still have those dark blue areas, which are minimum areas that a chase vehicle could use a small amount of delta V, but there's only 2 of them, and they're only at 2 pretty small time spans. And so this gives us, again, some really good actionable information. If you look over at the right here, we've got the departure time, the arrival time, and then the fact that it only takes 866 meters per second to go from Hyo to Geo. Next, I've got a Geo to Geo example. This is a fairly complex geo. This is across maybe 180 degrees or so. And again, I see a very small area up here that's a minimum delta V to get there. I've got 484 meters per second in order to intercept. But in this case, if I want to go ahead and perform proximity operations against that guy, it's going to take another 336 meters per second to stop my chase satellite and sidle up right next to my target satellite. So it'd be the addition of those two delta Vs that would allow me to prox up to that next guy. So those are one-on-one examples. Let's talk now about the many-on-many problem that I outlined earlier. So here's SOTA again. This is back on the analysis panel. And if you look at the chase vehicles and the target vehicles there, note that I've got 3 different chase vehicles, and I've got a number of different target vehicles. In the orbit diagram up here, you can see the chase vehicles are red. There's 3 of those, and I think there's about 11 different target vehicles here. And so this is kind of a smaller version, but it represents something you might see in operations where you might have a few threats against some assets that you definitely want to make sure you know what's going on for your targets there. So after you click the calculate button on those, you get results back, and in the results panel here, notice there are multiple different rows down at the bottom. So each one of these rows represents a different pair, a chase vehicle and a target vehicle. And what we've done is we've calculated delta V's to intercept for all of those. There's delta V's to prox in there. The times of interceptions are all there. But I've got so many of these, I don't really know which one is the one I need to pay attention to. And that's where the Vanguard number comes in. I had talked about creating a risk metric, a risk evaluation that allows you to quantify which pairs are the ones that you need to be worried about. And so this Vanguard number that we've invented is this risk evaluation metric. So when you do a many-on-many analysis, the results in this table here are sorted by Vanguard number. The smaller the Vanguard number, the more imminent the risk for your satellites. So in this case, Vanguard of 6.4 happens to be the smallest. And that represents, again, the Vanguard in this case represents the amount of delta V to get my chase to my target guy. The smaller that is, the more of a risk it is. And the amount of time for my chase guy to get to my target guy. The smaller that is, the more of a risk it is. So the smaller the Vanguard number, the more of a risk you have. The orbit display here just shows the orbit path that the chase vehicle will follow once it executes that maneuver and intersects your target there in the green. So let's talk a little bit more about that Vanguard number. This is a plot with many hundreds of different satellite pairs. And the Vanguard number, again, shows when you plot it in order of Vanguard number from low to high, it shows you very easily which ones are the most vulnerable chase target combinations. And you can take those right now and you can start acting on those particular pairs because those represent the highest risk to your satellite from those chase vehicles in your analysis. And so the Vanguard number is really a nice way to understand what's important right now. Once you understand what's going on with these 4, you can start looking at the ones a little bit higher up. You maybe have a little bit longer time, or maybe it's going to cost more delta V for these to be a problem. But once you have this Vanguard number, you've got information you can act on pretty fast. Okay, so that's SOTA. That's what's in SOTA today. There's some features we have in beta that we're working on direct ascent ASAT analysis I'd like to talk about for a minute. And this is another video. I'm going to start playing this, and I'm going to pause it to talk a little bit about what's going on here. And so here in the purple is direct ascent ASAT just after burnout, so that it is now headed to Geo. It's in a GTO orbit here. It is heading to Geo, and notice that in Geo we've got sort of a gridded up set of colored dots. And what I'm showing here is the risk to Geo from this ASAT, assuming this ASAT still has additional delta V capabilities. And it could perform another maneuver on its way up up to a certain maximum. In this case, it's 1 kilometer per second. And these dots represent the risk to that particular region of geo if it were to execute a maneuver at a given time. And so you'll see these dots change color as time progresses here in the video. And I'll go ahead and start this back up. So that dots that are far on the edges are a pretty low risk because it would take the full kilometer per second to get over there if it was to do it a new maneuver at that particular time, now, for example. A high threat are these magenta colors in the middle because it would take a very small amount of delta V to get there if it was to perform it at that given time. The white dot here is where it's heading if no additional delta V is applied. But immediately when you look at this, you can see that there's a pretty wide span of geo that can be affected by ASATs. If they have additional delta V capability, I'm gonna play that one more time. If they have additional delta V capability, there's a pretty wide swath of geo that is at risk from those. A kilometer per second isn't undoable. It's something that can be done. And so looking at this gives you kind of a new insight into what kind of threats you might be seeing. So we'll let this play out again. Even as it goes past the geo belt, coming back down again, there is still a pretty good swath that can be affected by the delta V from this guy. All of it's visible right now is still in the threat zone for this ASAT. Okay, so now let's do a SOTA demonstration. So let me bring SOTA up here. Okay, so this is the SOTA tool. It's got a globe here that shows that I have a chase vehicle already loaded, and you can see I've got the single chase vehicle down here. I've got a date set in here of September 1st, 2016, start time 1700 hours. I want to go for 4.5 hours. Here's the engagement type, intercept or proximity operations. I'm just going to select intercept for now. If you do want to perform a plane match, you can check this plane match first box, and SOTA will calculate a plane match delta V for you, and then calculate the intercept delta V as well. If you just want to understand what the differences are between plane matching first and not plane matching, you can use this. So let's go ahead and add the target vehicle. I do want to point out that you can add information about your satellites, ephemeris from your satellites, in a couple of different ways. You can do that from a file. It might be a .e file from SDK, or a TLE file, or a TCE file that contains many different satellites for the many-on-many problem. If you have SDK, you can have it connect directly right to SDK. It'll pull up a list of all the satellites that you have in SDK, and you can choose from one of those. Or from our SSA software suite, our SSS tool. If you have access to that, you can connect directly to that and pull ephemeris data right out of that system as well. So I'm just going to do the file right now. I'll bring this up. I'm going to load the target.e file. And it says target. I'll add the vehicle. And then we can see the target orbit in green. This is the complex LEO to LEO case that I showed at the beginning of the webinar. So everything's set. I'm just going to go ahead and hit calculate. And then we'll look at the results for this particular complex LEO to LEO. I apologize if there's any kind of lagginess. It's not lagging on my computer. It's most likely due to the GoToMeeting that's running as well and the network bandwidth issues that we have. But I'll go slow, and hopefully you'll be able to see everything just fine here. But so here's a plot inside SOTA of the surface plot of those wells that I had talked about before. There's our departure delay, and there's our time of flight in hours, and here's our delta V as well. That's our 3D surface plot. We can look at the contour gradient plot as well and see the different possibilities for small delta V's. And so the dark blues, again, represent minimums there. And then finally, our orbit visualization here as well. So our delta V to intercept at this particular case was 250 meters per second. Our delta V when it applied, after the maneuver is applied, let me go ahead and fast forward this. After the maneuver is applied, the chase vehicle is on an intercept course, and there you can see it happen. Let me go just a little bit slower. The chase vehicle is on that intercept course with the target, and it does intercept the target. And so it doesn't take much for that guy to get there. So let's go back now. Let's take these two vehicles out, and let's do a many on many. So I'll add vehicles again from the file. And I'm going to add a TCE file, which contains multiple TLEs. In this case, I've got 3 different chase vehicles. I've got some warnings on the right telling me that my ephemeris for these is not in line with my start date over here. So that's good information. I need to go change my analysis time if I want to use this ephemeris data. So I'll do that now. And since these are geo, I'm going to make these 24 hours. And then I can see these 3 chase vehicles in geo here. Now I'll add some target vehicles, same thing from files, and I'll add the geo target TCE file that I have. And again, that has multiple different satellites in here. Let's add that. And then those show up here as well. Let's go ahead and keep this on intercept for now, and we'll just hit calculate, and we'll go look at the results. So when you do a many on many, the very first thing that comes up in the results panel is a Vanguard plot. So you can see immediately which ones are a threat to you. So again, I mentioned they're sorted by Vanguard number. So here's a Vanguard of 6.3. So this chase 3 vehicle chasing 33749 is something I should be looking at right now. I've got a time of intercept of 12:08 on the 7th. So my initial analysis start time was the 6th at 1700. So I've got a little bit of time, but not much. So I need to start looking at that one right away. The next one is the 7th at 1600. And so again, a little bit more time, but it does tell me something I need to look at right now. So here are the delta V contour gradients for the different pairs. Let's go to the surface plot here. These always have some nice texture to them. And as you scroll down through the results, you can see how the different pairs have different delta V characteristics for departure time and time of flight. And then finally, we have orbit visualizations as well for these guys. And again, these are showing the orbits after the maneuver that the chase vehicle is going to be executing to intercept with the target vehicle, since we did intercept there. One thing I want to point out is that you can export these results. So I can export all of the plots in the CZML for this pair. By doing that, I just have to select a folder, and all of those, all the data and plots will show up in that folder. And so let's look at that. I'm going to go ahead and bring up the folder here. This is some exported results. And what I'd like to do is show you what you get once you export. So you get a CZML file. If you're not familiar with CZML, it stands for Cesium Markup Language. Cesium is an open source 3D visualization globe that you can see here at cesiumjs.org. So what it gives you is the encounter after the maneuver has happened. And so let me just bring this back up here. And so I'm going to actually drag this over here and create a new one. There we go. So I've got the target and I've got the intercept. And as I drag the little scroll piece down here, we can see that they are moving along. And this was not quite an intercept at this node, but let's go watch the next node. This looks like it's going to be the intercept here. And so this CZML file contains all of the information that you need to show this 3D visualization. The Cesium is a free product, so you can have Cesium in your organization to view these if you need that, or for the people that you're trying to provide this analysis for. Let's see what else we have here. There's an ephemeris file, a .e file that shows the post-maneuver ephemeris for the chase vehicle. We have plots that you can plot that look just like the plots inside the tool. So here's the delta V plot for the complex Leo that we looked at. And here's a surface plot. That you can then, rotate around and look at the surface values for that particular case as well. There is a file in here that shows you the number of minimum delta V's. This is actually a different file. I'll get to the minimum delta V file in a second. This file I opened up is all of the delta V data. So for every possible orbit type that we looked at, and that heat map that we looked at, this guy here. This data represents this heat map. This is all the heat map data in this file. So this minimum delta V opportunities file is one I mentioned earlier. This one shows you the minimum delta V's for these different wells here. So this represents these small wells, and this is tunable. You can say, I want to see delta V's that are within 20% of the minimum delta V, or 50%, or something like that. And so the values that come out of here tell you what these opportunities are. They tell you what your delays are and your time of flight. So this gives you information you can plug into our tools or other tools right away, like SDK. And then finally, you get a file here that shows you the exact technical information for these maneuvers. We've got a departure time for the minimum delta V and the arrival time. So here's our arrival time of 19:53:44, which should match up with what we were seeing over here, 19:53:17. Come over here, it's 44:43:44. The delta V's, the minimum delta V's are here also. So these are the delta V values that you can plug into a tool like Gator, AstroGator inside SDK, and have it then perform for you all the calculations you need to get operational values out for your burns if you need to do anything like that for your defensive operations. So that's the output there. I don't think there's anything else I needed to show you there. So I think that's about the end of my SOTA demonstration. Let me go back to the charts here and just do a quick summary. So really, the time of relative safety in space, unfortunately, is coming to an end. The threats that we have are real. They've been acknowledged. We need to assess what those threats are, and those assessments must be accurate, fast, and customizable. SOTA is a tool that we've developed that runs hundreds of millions of calculations in minutes to let you understand what those threats are. It locates the most likely threats to a given object, and the results will show times when that threat is possible. The Vanguard number is that risk valuation that will identify the highest risk pairs of space objects for you automatically. And then we've got customizable threat types in development as well. So that's something you can look forward to, including that ASAT analysis.
Great, thanks guys. And with that, we have our Q&A section of the webinar. You guys have asked a lot of great questions, and we will try to get to as many of them as we can. The first question being, can SOTA be used with simulated data?
Yes, it can. And so some of the data that you saw me using today is simulated data. I just generated some orbits inside SDK and wrote those out as ephemeris files and use those to assess threats. So yeah, absolutely, you can use simulated data.
Great. And next question, is it possible to use the results of SOTA in SDK with AstroGator?
You can. In fact, let me go back and show you that file again. This file here is part of the export, shows you the kinetic delta V's for intercept or the prox delta V's for the proximity operations that you can use and use these to seed Gator with. Again, you can bring those right into Gator and you can perform maneuver operations inside Gator and do operations with that tool. So yes, absolutely.
Thanks, Ted. Next question. can I get access to a beta copy of the ASAT capability for SOTA?
You can. We do have that in beta right now, and we can deliver that to you. If that's something you want to look at, please get a hold of us and work out how to get that to you.
Awesome. Next question. Please describe the Vanguard number in more detail. And the second part to that is, can I customize what goes into it?
Sure. Let's go look at that particular slide. Let me bring that up here. So this is a Vanguard plot. I'm going to go to a different slide that shows the output of all the different many on many here. So there's a Vanguard number here. The Vanguard number is a metric that we derived that takes into account two constraints currently. The first constraint is how much delta V is being used by the chase vehicle to get to the target vehicle. And the second constraint is how long is it going to take the chase vehicle once it's maneuvered to get to my target vehicle. And then we combine those two different constraints in a quantitative way to come up with one number, and that's the Vanguard number. We are working on ways to tune that Vanguard number so that you can add any other types of constraints similar to what SDK might have, and allow you to make the Vanguard number be more meaningful for your particular situation. So right now it's based on those two constraints, but we are working on more. It's in development now.
Thanks, Ted. And another question is, what file formats can be used to define the threat and target vehicles?
That's a great question. Let me go back to actually go to SOTA. So here on the chase vehicles, I talked about the source. You can do a source from file or SDK or the SSA software suite. On the file section there, you can bring in, like I said, TLE files. So a .tle file you might get off of Celestrak or might get from SDK. You can bring in .e files, which are SDK generated files. Let's see, TCE files I mentioned. Those are the three file types that I think we take in today. We do have plans to bring in additional ephemeris type files, but those are the three we support today.
Great, thank you, Ted. Thanks for joining the webinar. Thanks to Ted for hosting, and thank you to all for joining us today. For those questions that we didn't get to, we will be answering those individually after we sign off. And we will also be sending you all a recording of this webinar after. Make sure to sign up for our next webinar on January 23rd on test, training, and exercises for space professionals. Thank you guys so much, and we will see you next time.